Hello friends and students, I hope you have understood the working of a full wave rectifier. The link for the full wave rectifier explanation has been given in the description. Make sure that you go through the video. Now when we talk about a full wave rectifier, we have two different kinds of full wave rectifiers. One is a full wave rectifier with center tap transformer, and the other one is a bridge rectifier, which is also a full wave rectifier. Now, after having understood the operation of a full wave rectifier, let us solve a few problems. So here we shall take a few problems considering a full wave rectifier with a center tap transformer. So let's go through the first problem. The first problem states that a full wave rectifier using two diodes is supplied from an AC given by 220 sine 314t volts through a center tap transformer of turns ratio 10:1. RL equals 1000 and RF equals 20, and we need to calculate a few parameters. Now, given a full wave rectifier using two diodes with a center tap transformer. So if you do remember, this is the transformer primary, and then you have the secondary, and then you have the center tap. So if the voltage here is V1, let this be V2. So here V1 is given. What is V1? V1 is 220 sine 314t volts, and we have the turns ratio. So we know that N1 by N2 is nothing but 10:1, which is given in the problem, and that is equal to V1 by V2, where this is V1 and V2 is the voltage across the transformer secondary here. So therefore I need to find V2. So what is V2? V2 is V1 by 10. So which is 220 sine 314t divided by 10, and that gives us 22 sine 314t volts. Now let me compare this equation with Vm sine omega t. So when I compare these two, we realize that Vm is 22 volts and omega is 314, where omega is 2 pi f equals 314. And what is f? F is 314 divided by 2 pi. So we get the value as 50 hertz. So therefore the frequency is 50 hertz. And what else has been given? It's been given that RL, the load, is 1000 ohms, and RF, the diode forward resistance, is 20. Now if you do remember the working of full wave rectifier, so in the top path we have one diode, and here in the bottom path also there is another diode. So in the positive half cycle I have the first diode which is conducting, and in the negative half cycle I have the second diode which conducts. So therefore in each cycle only one diode is on, so therefore we only have RF. So in each of the half cycles the forward resistance to be included is RF only. But whereas in case of a bridge rectifier, we have two diodes which are on in each cycle, either the positive or in the negative cycle. So therefore there in that case I would get 1 plus 2 RF by RL. So I've already listed all the formulas. I hope you do remember these formulas. So let us find the first one. We need to find the average load voltage, which is VDC. So VDC is 2 Vm by pi divided by 1 plus RF by RL. So let me substitute the values directly. 2 into Vm is 22 by pi divided by 1 plus RF is 20 divided by 1000. So make sure that you do the calculations correctly. So we get the voltage as 13.73 volts. Next B, I need to find IRMS. Right, so we need to find the RMS current. So IRMS is nothing but Im by root 2. So we need to find Im by root 2. So to find Im by root 2, I need to find Im. So what is Im? We know that Im is nothing but Vm divided by RF plus RL. So the maximum voltage divided by the total resistance in the given circuit, which is the load, along with the forward resistance of the diode, which is equal to 22 divided by RF is 20, RL is 1000, so it is 1020 amperes. Right? So therefore this is equal to 21.57 milliamperes. So this is Im. So once Im is known, I can find IRMS. So IRMS is this value 21.57 milli divided by root 2. So we get the value as 15.25 milliamperes. So I'm writing the values directly. So make sure that you calculate and get these values. See, I need to find PIV. So the peak inverse voltage, PIV, is nothing but, so remember, in case of a full wave rectifier using a center tap transformer, the peak inverse voltage is nothing but twice the maximum voltage, which is 2 into 22, which is equal to 44 volts. Next, let us find PDC. So the DC output power is nothing but VDC into IDC, right? Or it is equal to VDC square by RL. So remember, we already have VDC and there is no need for us to calculate IDC because RL is already known. So we know that power is voltage into current, or it is also equal to V square by R. So it is VDC square by RL. So we have VDC, which is 13.73 the whole square divided by RL is 1000. So we get the value as 0.1885 watt. And the last one, what is the output frequency? The output frequency is nothing but 2 into 50, which is 100. So we know that this is the output of full wave rectifier. So therefore the output frequency is twice the input frequency, which is nothing but a sinusoid or a sine wave. So therefore it is 2 into 50, which is 100. So let's go through the next problem, which is very interesting. We need to show that the maximum DC output power. So the DC output power PDC is nothing but VDC into IDC. So power is voltage into current. In a full wave rectifier occurs when the load resistance RL equals the forward resistance RF. So we need to show that there is maximum power delivered to the load when the load resistance RL equals the forward resistance RF. So again we have PDC equals VDC into IDC, or it is VDC square divided by RL. Right, because we know that IDC is nothing but VDC by RL. All right. Now what is VDC? From the given expression, I have VDC is 2 Vm by pi divided by 1 plus RF by RL. Now let me try to substitute this value here in the expression. So we get the value of PDC as VDC is 2 Vm by pi divided by 1 plus RF by RL. I need to square this term divided by RL. So let us square this term carefully. We get 4 Vm square divided by pi square. And then here I get RL plus RF the whole square divided by RL square. Right? So if I take the LCM, I get RL plus RF by RL. So I'm taking the square for this denominator. So I get RL plus RF the whole square divided by RL square into, what do I have? 1 by RL. So 1 RL I can cancel. So we get the expression as 4 Vm square divided by pi square into RL plus RF the whole square into RL. So this is PDC. Now we need to show that maximum power is delivered to the load when RL equals RF. Now how do I find the maximum power? So we know that the PDC, that is the power delivered to the load, is nothing but the function of the load resistance RL, isn't it? So therefore, to find the value of RL, so I need to find the value of RL such that the power delivered is maximum. PDC is maximum. So how do I do that? I find differential of PDC by differential RL and I equate it to 0. So if I differentiate this expression and equate it to 0, then I would get the value of RL such that PDC is maximum. So differentiate this expression with respect to RL and equate it to 0. So when I do that, what do we get? Now all these terms can be treated as constant. So we have 4 Vm square divided by pi square. And then I have this term RL divided by RL plus RF the whole square. So we have square of the denominator, and in the numerator what do we have? We have the denominator, that is RF plus RL the whole square, into differential of numerator, which is RL by DRL, which is 1, minus the numerator, which is RL, into differentiation of the denominator, which is 2 RL plus RF. So let me repeat this. So I need to differentiate RL divided by RL plus RF the whole square. So according to the formula, we know that it is the denominator square. So this is the denominator square, and then in the numerator I have denominator into differential of numerator, which is differential of RL, minus numerator into differential of denominator, and this has to be equal to 0. Now observe that if this expression has to be equal to 0, then the numerator has to be equal to 0. Now I cannot have 4 Vm squared by pi square equal to 0 because they all are fixed values. So this is not equal to 0. So definitely I have the numerator, which is RF plus RL the whole square minus 2 RL into RF plus RL should be equal to 0. So let me take this term to the other side. So we get RF plus RL the whole square equals 2 RL into RF plus RL. So RF plus RL gets cancelled. So here what do we get? RF plus RL equals 2 RL. I take this RL to the right hand side. So I get RF equals 2 RL minus RL becomes RL. So I get the expression where the forward resistance equals the load resistance RL. So for the condition when the forward resistance of the diode equals to the load resistance RL, then we have maximum power delivered to the load. So this is what we have proved. So it's very simple. You start with the expression of PDC. PDC is VDC into IDC, or it is VDC square by RL. So using this expression, we substitute the value of VDC in the expression here, and then to show that maximum power is delivered to the load only when RL equals RF, differentiate the expression PDC with respect to RL and equate it to 0. So when I equate it to 0, I have to equate the numerator, and finally we get RL equals RF. So we have solved these problems under full wave rectifier. So do like, share and subscribe, and press the bell icon to get notifications of all the further uploads, and to watch the operation of full wave rectifier as well as bridge rectifier. The links have been given in the description. Do watch them so that you will have a clear understanding about the working and the operation of a full wave rectifier.